next speaker for today is Boris Konopelchenko from Salento, who will talk on discrete deformations and associative algebras of associative algebras and discrete systems.
Well, first, I would like to thank organizers for kind invitation, possibility to give a talk here, and also for very warm hospitality of the Institute. It's a very nice place. It's a real pleasure to be here. And for me, it will be very important to present some results, and I hope very much that you say that something is known, the main goal, probably something new. So I will speak about the discrete deformations of associative algebras and discrete integrable equations. Why integrable equation? Why discrete? I shouldn't explain. Everybody's speaking about that. And why associative algebras? At least by three reasons. Algebras are very simple objects. Second, it's already well known that some basic relations in the associative algebra, like associativity condition for structure constants, encode some basic relations in different theories. For instance, for two-dimensional topological field theory, just encode relation between the correlation functions. I'll try to show that there are other cases like addition theorem for tau function or bilinear Hirota-Miwa equation for KP hierarchy, say phase 3-second formula, Menelaus relations, very old theorem, about 2000 years old, are nothing but the associativity condition for certain algebras. Moreover, third reason is that deformations of associative algebras produce discrete equations. And I did mention connection with the 3D consistency, which has been definitely discussed here. And I will say at the very end some words about that. In mathematics, deformations of algebras is very well established subject. In fact, going back to the classical works of Gestenhaber, 40 years, more than 40 years old, almost the same age as the soliton theory. In one of his approaches, he formulated the following thing. Let's consider algebra, but not algebra, but algebra in a given basis. It's just citation. To take a point of view that the objects being deformed are not merely algebras, but essential algebra with a fixed basis, and to treat algebraic set of all structure constants as a parametric space for deformation theory. Since that time, almost nothing has been done explicitly along this approach. The idea is, of course, simple. Let we have algebra. Let's denote Pj, P0, P1 up to Pn basis in algebra. This is table multiplication. An idea to consider structure constants as a function of some deformation parameters. Of course, you can say, okay, let's assume the functions, some functions. Usual question, where from to take these functions in such one or reasonable way. And remarkable example of this type of approach, not of this type of approach, which demonstrates a very non-trivial example of this type, has been found by Witt and Dijkgraaf, Verlinde and Verlinder. Within the two-dimensional topological field theory, they showed that correlation functions in this theory should obey some crossing relation. And these crossing relations are nothing but by the associativity condition for structure constants of certain algebra of so-called primary fields. Then they showed also that if you consider perturb theory, then the structure constants should have such a form where F a free energy, and then with this substitution, associativity condition where C expresses certain derivatives becomes famous WDVV equation. So this was the first, to my knowledge, example which shows if you consider deformation of the structure constants, this deformation can be described by nonlinear PDE. It will be just nonlinear PDE. It's non-integrable. It was the first example which, in fact, was a beginning of pretty long story. Not that long. It was 90. The first interpretation, formalization of this approach is very well known, was done by Dubrovin in terms of the Frobenius manifolds. So in this case, one can describe deformation of so-called Frobenius algebras, algebras with some specific property. And then there was several extensions and generalization. One which follows in 7 years was so-called theory of F manifolds proposed by Hertel and Manin, where they considered this type of deformations, but without considering specific algebra, just algebra which acts in the tangent space. And multiplication is defined as, roughly speaking, tangent space for the manifold. They wrote down equation, discuss the property, and so on and so forth. This theory of Frobenius and F manifolds has been shown has a number of applications in different fields of mathematics and mathematical physics. Okay. I will discuss it, it's pretty well known and written even books on that. Instead, I will show that recently with Franco Magri we tried to develop another approach to deformation of associative algebras. We began with so-called coisotropic deformations. I will say a few words about that. Then this approach has been extended to other types of deformations, quantum deformation, discrete deformation, or more generic deformation defined or generated by certain algebra, the algebra. I shall remind you something about the so-called coisotropic deformations. So again, let's have finite dimensional algebra. Let's choose the basis in this algebra. This is a table of multiplication which defines structure constants. This is just associativity condition. Now, let's try to describe deformation. So first we assume the structure constant depends on some parameters, x. Okay? And how to describe this main point? In fact, we use basically the ideas of classical mechanics. Let's associate with elements of the basis of the algebra and deformation parameters, set of numbers, p and x. Then let's consider this set of functions which somehow represent table of multiplication. Then we assume that p and x are nothing but the Darboux coordinates in two n-dimensional symplectic space, so just canonical Darboux coordinates. Okay, with respect to canonical Poisson bracket. This is a basic point. Identification of the elements of the basis, deformation parameters with Darboux coordinates in symplectic space. Then we consider submanifold of zeros, of common zeros of all these functions. Let's call it gamma. One can consider also ideal created by these functions. Let's call it J. And let us assume that this ideal is closed. So Poisson bracket between arbitrary two elements of this ideal belong to the ideal. Okay, F, J, K form a basis. So this condition is just equivalent to the statement that Poisson bracket between two different F. It's linear superposition of the same F, elements of the basis. In this case, this submanifold gamma will be nothing but the coisotropic submanifold. Very well known object, very well studied. It's just, in fact, one of the definitions of the coisotropic submanifold in symplectic manifold. This requirement, in fact, imposes very strong constraint on the structure constants. If you will do the direct calculation, one can show that this condition is satisfied if structure constants obey the following system of equation. We call it bracket. Okay, there are 6 terms, quasi-linear somehow, equal to 0. Then, of course, we have to add condition of associativity, and this equation written here, and condition associativity form so-called, we call it central system, which describe deformations of structure constants. Any solution of this system describe coisotropic deformation of the structure constants for our given associative algebra in a given basis. Okay, I would like to save some time, say this system in fact appeared implicitly in the paper of the Hertel and Manin. They never wrote explicitly it, but one can show it's exactly the same. this system equation, it was shown by Franca and myself, contains number of integrable systems, so-called dispersionless system. From oriented associativity equation, WDVV, hydrodynamical type systems like dispersionless KP, dispersionless other systems, and so on and so forth. For instance, the DKP hierarchy with number punctures, n punctures on a Riemann sphere. So it's just a simplest example, so-called universal Wisdom hierarchy. And there are other examples which has been discussed previously in terms of Frobenius F manifold somehow by Dubrovin, Krichevich, Givintad, and many others, and some others. So this system.
There are so-called dispersionless Virasoro constraint known for connection with.
No, okay. At the moment there is no. You can impose it. There will be sort of additional constraint.
They are automatically satisfied.
Sorry.
They are automatically satisfied.
For solution of this system, not. No, you should impose it to characterize tau functions and so on. Okay, this system equation effect has a very long story. For the first time, it has been found by Jan Aqua more than 40 years ago in the study of so-called differential concomitants. Okay, differential concomitants are pretty known things, all things almost forgotten now. For one tensor is sort of should be, it will be a sort of Nenhers bracket. And they ask the question, what will happen if you consider 1, 2 tensor or 1 n tensor? And they found pretty interesting thing to construct the differential concomitant. So expression linear in the first derivatives, which contains 1, 2 tensor, the simplest case. Well, we have exactly the expression I presented before. In this construction, one can show that structure constants are nothing but the 1, 2 tensor. This system is just direct calculation invariant with respect to this system it has a tensoral character, so it's invariant as an arbitrary change of variable x. And this expression for bracket, in fact, has been written by Jan Aqua, and they showed it completely different way. So better to call this system as Jan Aqua or Jan manifold, as you like. Okay, I should leave it. So the basic idea was to associate with the element of the basis of the algebra and deformation parameters certain algebra. In this case, it was Poisson algebra. And then, from the requirement or closeness of ideal, or from the condition that submanifold gamma is not empty, one has system of equations which characterize structure constants, which define deformation of the algebra, so-called coisotropic deformations. Advantage of this approach, from my point of view, was that it was formulated completely on the level of classical mechanics. Phase space, momenta, coordinate, first class constraint, fjk equal to 0, and it will be quite natural to extend to quantum case in very trivial, say, almost trivial way. Just substitute Poisson algebra with algebra Gazenberg. That means substitute p and x, these operators, p and coordinate. And it works in this case with some point, I would like to say. Again, now we have to consider non-commutative algebra. Before it was commutative, but we will assume the basis, it admits the commutative basis. There are algebras of that type, for instance, algebras of differential operators. So we again have the basis, deformation parameters, and we establish the correspondence between the elements of basis, deformation parameters, and set of operators, which obey the commutation relation for Gazenberg algebra, and this is a constant, Planck constant. Now, as a previous case, let's consider the following set of operators. Now the operators, all dependence on x put on the left, usual rule in quantum mechanics. Now we have to say something about this set of operators which represent the table of multiplication. If we will require that all these operators are equal to 0, one can see immediately it's too much, too restrictive. Calculating commutator of this fjk with momentum, we immediately will see the derivatives of all structure constants are equal to 0, so no deformations are allowed. this constraint is too strong. Way to go out to have something non-trivial, in fact, goes back to the classical works of Dirac. I already said that in classical case, for coisotropic deformations, f, j, k are nothing but the first-class constraint. And in 50s, Dirac found a way how to quantize first-class constraint. If you they needed it to discuss the degenerate classical theory. Prescription or recipe of Dirac was to use the first-class constraint, now operators, to select subspace in Hilbert space of states by the following formula. It's just standard classical Dirac recipe. Okay? And now we use the same recipe. We will say the structure constant C defines the quantum deformation of the algebra if these operators have non-trivial common kernel. This means that this set of equations has a common solution. And one can show similarly that this constraint, this property impose certain constraint on structure constants. Okay, to derive them, one can use the following identities, just identity for operators with some n and omega. And if you consider associative algebra, this difference vanish. And if we apply, that means that, okay, now apply the rest. I missed the point here. To psi, f st applied to psi equal to 0. So what's remain? This operator times psi equal to 0. Okay? And this condition will be satisfied. I'm sorry for this misprint. If this omega t, this system of equation vanish. How to calculate?
Not vanish, it vanish only on this vector. It's a partial solution.
No. He's missed, I'm sorry. You will have here that one. Okay? So if omega equal to 0, this condition will be satisfied. How to find omega? Very simple. Just use property of operator P. It's very well known for anybody. Commutator of P with any function is just derivatives with H. And I would like to emphasize that here P is not operator of derivatives. It's just a member of the Heisenberg algebra. Anyway, it will be valid like that. Using all that, one can show that omega has the following form. Old form, which appears in associativity condition, this additionals is proportional to H. This system of equations which govern quantum deformation of associative algebra. Any solution of the system produce quantum deformation of associative algebra in a given basis. Okay, this system has very nice, very simple and clear geometrical meaning. One can show it's again invariant under the general transformation of coordinates. And the C transformed like a Christoffel symbols. And of course, here is nothing but the Riemann-Curvature tensor. So the meaning of the central system is a vanish of Riemann-Curvature tensor for structure constants identified with the Christoffel symbol. And there are many solutions. Okay, I hope I should go faster. Again, one can consider subclass of deformation where associativity condition is satisfied globally for all values of x. This will produce immediately oriented associativity equation, WDB equation, but there are other deformations for which associativity condition is not satisfied globally for all x. Among them, for simplest case, n equals 3 is Boussinesq equation, standard Boussinesq equation. For infinite dimensional algebra of certain basis, one will get KP hierarchy, standard KP hierarchy, multi-component KP hierarchy, many other systems, including classical Darboux system. These were two basic examples of deformations. Coisotropic and quantum deformations, this give rise to dispersionless integrable system and dispersive integrable system. And now we will pass to general scheme. Again, let's consider finite dimensional algebra, non-commutative. It will assume there exists commutative basis. I will denote the elements of basis in this way. Table multiplication. For commutative basis, we have the following property. If algebra has unit element P naught, then this value of structure constant is just delta function, or Kronecker symbol. We introduce now again deformation parameters. Now it should number of deformation parameters can be different from number of dimension of algebra. And now we'll try to describe deformation. First, let's consider the algebra B of the dimension n plus m defined by the following commutation relations, where E alpha are basic elements of this algebra. Next step, to identify elements of the basis of our original algebra and deformation parameters with the elements of this algebra in certain way. Of course, there are different possible identifications. One, this identification will define so-called deformation driving algebra. I call it DDA. Next step, third, again consider elements which we already have seen. That one, they definitely belong to the universal developing algebra of our algebra U, our DDA. Now we will require that all these elements are non-zero left zero divisors, and in addition they have common right zero divisors. I will remind you what is definitions. Very simple. Elements A and B are called left zero divisors and right zero divisors if they obey the following property. And of course, A and B should be different from zero. There exist such elements, and we require exactly this property. In this case, if we consider the left ideal generated by FJK, they form left ideal of left zero divisors. And our definition will be the following. Structure constant C defines the deformations of the algebra generated by given DDA if FJK all are left zero divisors with a common right zero divisors. This means that for all FJK exists such psi such that this equation is verified for all values of indices. It's reminds very much this Dirac recipe, but now it's on the level of algebra. And in the rest, I will consider a case when all P commute between each other, all X commute, and commutator of P and X, it should be algebra. Of course, now we may have only the following form. Why? Because I began with algebra with commutative basis. So P should commute here, and here I assume that deformation parameters also commute, not to discuss the non-commutative case. With this choice of DDA, one can show again demonstrate the following identity, where n set of a function of x and p, and omega depends only on x. Moreover, in this case, commutator of p with c is given of the following form, where delta, some operation, depends only on x. Explicit form of this delta depends on DDA, but nevertheless it depends only on x in all cases for DDA of that form. Now let's consider this equation. Okay, apply. This is equal to 0 for associative algebra. Apply from the right psi. This term will disappear, and what we will have? We will have the following equation written here.
The deformed algebra is not associative.
Sorry?
The deformed algebra is not. So you have commutative.
Yeah, as in quantum, it's not associative now. Deformation, in general, not associative. They do not preserve associativity globally, in general. Well, so we have this condition, and omega has the following form, explicit form. Again, simple term, and there's this additional term. Of course, if omega equal to 0, all these conditions would be satisfied, so this condition is necessary. Under some technical assumptions, sort of genericity, one can show it also will be a sufficient condition to satisfy that fjk will be left divisors of zeros. Okay? So I shall call this system a central system which defines deformation of our algebra generated by given DDA. Of course, different choice of DDA give rise to different central systems. But I would like to emphasize that here, set of the structure constants is the same, algebra is the same, set of the structure constants is the same, deformation will be different depending on the choice of DDA. Okay, and examples I considered before correspond to the choice of DDA as a Poisson algebra, and if we choose DDA as a Heisenberg algebra, we'll consider quantum deformation. There are other examples, probably I will discuss it next seminar. Most simple case, probably when we consider DDA as a three-dimensional algebra. So we will have one deformation parameter. You can repeat all the scheme, one will end up with equations, system of equation of ordinary differential equation or mappings, and system of differential equation in fact contains set of equation for Chassis-Bureau list of the third order equation, ODEs, with Penlever property. I will skip all of that. Now I will consider go to discrete case, which I want to discuss. If you would like to have discrete equation, our algebra DDA should reproduce discrete central system. And of course, it's quite natural to begin with the algebra of shifts or differences. I will consider abstract algebra as a DDA which have with the following commutator relations. Of course, one realization with this algebra is that nothing but the algebra of the shifts, standard shifts in variables, okay? Where t, j, x of the function is a standard way. Another realization is algebra of the differences, not algebra of differences, the following algebra, okay? If you put all epsilon parameters, epsilon j here equal to 1, it will be algebra of differences. Again, it has standard realization. I will consider a little bit more general with some parameters. Again, it's very well-known thing, which may vary, take any values. In case epsilon j equal to 0, what we will have? P naught will be I shall consider always the case, it will be a central element of the algebra. You can choose it always as 1. We will have Heisenberg algebra. If epsilon j, all epsilon j equal to 1, we have algebra of differences. Okay? It's written here. So considering this algebra, we will have central system which interpolate in some sense between Heisenberg algebra and algebra of differences. So it should have something in between or containing both cases, quantum deformation and discrete deformations, as we will see. This somehow give a way to discretize dispersive equation, as we will see. Okay, now let's consider central systems. Well, in the first case of algebra of shifts, central system has the following form. This is standard shifts. In the second case of difference, the following form. Okay. Geometrical interpretation, probably I shall skip because I have no time. As I mentioned, in quantum case, it has a meaning of vanishing of Riemann tensor. It has, in discrete case of the second case of differences, exactly the same meaning, but in discrete case. One can show it's observing, rewriting central system in terms of matrices introduced in such a way, so-called covariant derivatives defined more or less standard way. And one can show that equation I wrote, in fact, omega in terms of matrix has the following form, and moreover, for these covariant derivatives we have the following identity with omega which appear here. So our discrete system, central system, is omega jk equal to 0 as a matrices. Okay, if you will recall what we know in classical case, if you consider standard continuous covariant derivatives, Riemann tensor is defined as a commutator of the covariant derivatives. And this is exactly discrete analog. So it's quite natural to identify omega with components of discrete version of Riemann tensor. So central system for deformation described by algebra of difference has a meaning of vanishing of discrete Riemann tensor. In fact, it's not new. It has been discussed before by several authors in different contexts. Now, I would like to present a simple example of this scheme. Let's begin with the three-dimensional algebras, P0 unit element, P1, P2. Table of multiplications has a trivial part and the following non-trivial part. Now I denote structure constants A, B, C, and so on and so forth. Okay, central system is the following system. Okay, where C1, C2 are matrices organized by structure constants. It's quite convenient to write it such a way. So we have the system of equation for 9 functions. I will not write it explicitly. I shall consider this particular case to show a concrete example. Let's consider the so-called Boussinesq gauge. Why Boussinesq? It will be clear immediately. So we choose B equals 0, C equals 1, G equals 0. It's admissible constraint. System of equation, central system is reduced to the following 3 equations, discrete equations with parameter. In limit epsilon 1, epsilon 2 equal to 0, so when we have the Heisenberg algebra, delta J becomes derivatives, shift operator becomes 1. This system of equation becomes the following system of three equations for E, D, and A. Is nothing but the following equation is continuous standard Boussinesq equation. Okay. So system I wrote on the top is sort of discretization of the standard Boussinesq. In the one particular case, it's continuous Boussinesq. When epsilon 1, epsilon 2 are equal to 1, both, it will be fully discrete Boussinesq. And there are 2 intermediate cases. All of them were considered before in different scheme. All of them are known, exactly correspond what is known about the discretization or mixed versions of Boussinesq equation. Second example, probably not that known. Let's choose G equals 0, N equals 0, C equals 1. Again, admissible constraint. I would not enter in discussion how to choose it. System reduced to the following system of equation. One can show that this equation implies the existence of function u, v, such that a, d, v has the following form. Now, this is just shift in one direction. A shifted in the second direction. In terms of u and v, our system becomes the following system of equation. In pure continuous limit, where epsilon 1, epsilon 2 equal to 0, we have it's reduced to a system of differential equations. It implies the existence of function f such that u, v, and b are the following form. And our system is reduced to the well-known famous WDVV equation. Okay, with some constant. Constant equals 0 is WDVV. In general case, we have the discrete version of WDVV, fully discrete, or mixed cases. Linear equations I wrote before, f, j, k applied to psi equal to 0, produce linear equations, linear problems, compatibility or condition of which give rise to the following system. In this case, it's the following system of equations. In continuous case, it has the following form, and in fact, it's basically essentially known. One can extract from the paper of Dubrovin very easily. It was not written explicitly, but essentially it was known. It was the case n equals 3 is simplest possible. There are many other cases which contains number of equations. Discrete KP, higher WDVV equation, then subclass of deformation which corresponds to discrete versions of the oriented associativity equation and different versions of associativity equation. For infinite dimensional algebra 1, we'll have the standard discrete KP hierarchy written in terms of potentials. So we see that in this scheme one can reproduce many, basically for me all known discrete integrable equations from the point of view of deformations of associative algebras. Previous cases were just standard algebras. Now I shall consider some special class of algebras where for the basis only multiplication of discrete element is defined. It's a very special case. I'll call it algebra again. This means that I have a basis in algebra, and the table of multiplication of the following form, with some structure constants. Okay? And I will assume that DDA, deformation driving algebra, again an algebra of shifts, not differences, but of shifts. Linear equations, which I wrote before, in these notations becomes the following system of equations with shifts. Now J and K shifts in Tj, Tk, and this is just indices for A. I'm sorry, it's not to confuse. One can discuss gauge transformation for these relations. I will skip all that. This system of relations clearly, or table of multiplication, contains the subsystem of any three elements because it's closed. Let's consider this. It has the following form, and I shall call the elements structure constants as A, B, L, and so on and so forth. This is table of multiplication for three-dimensional subsystem.
P1, P2 commute.
Yes, it's again a commutative basis. Okay, one can write down the central system, and I shall present it here. 9 equations. First 3 are pretty simple, rest is not that simple. First 3 equation implies the existence of the function u, v, and w, such that all the coefficients structure constant have the following form. And again, playing this gauge, one can choose different gauges to reduce number of dependent variables. Okay? And there is one really distinguished gauge given by this following constraint. It's not constraint, this is a gauge. Sum of A, B, L, so structure constants which appeared in the product P1, P2, equal to 1, the same for second as the third. It's a gauge. One can show any generic case can be reduced by gauge transformation to that one. In fact, this gauge has very nice geometrical meaning, sort of barycentric coordinates, very well known in classical geometry, very widely used. Okay, in this constraint, if I now parameterize u, v, and w in the following way, h1 is not a shift here, t1 is shift. This is just function h1 is 2 and 3. One can show that central system has the following form, or this form, and this is nothing but Darboux, discrete Darboux system, which has been introduced first within the debar dressing method, and then it was shown that it has nice geometrical meaning. It corresponds to this very distinguished gauge. Well, more specific case. Let's consider three-dimensional algebra, but without unit element. So there is no P0 here. We have only 6 structure constants. Again, we have all the properties. First, let's write down the associativity conditions, which is in fact, these conditions for P. We have the following condition for all structure constants, very simple. One can do the following observation, that this system of 3 equations, that one, in fact is equivalent to the single cubic equation and one of these equations. In generic case, when all structure constants are different from 0. Okay? This is just absolutely equivalent. Why it's important? Because this constraint is gauge invariant. We have linear problems. Of course, if we consider global rescaling of elements, it's just trivial. Well, we can do gauge rescaling which is local, depends on the points. It will be local transformation, it's called gauge transformation. Generically, associativity condition is not invariant under the gauge transformation, general gauge transformation. But this relation is invariant due to this identity. So in associativity condition, one can select one equation which is gauge invariant. Well, let's write down here system of equation, corresponding system of equation. One can recognize it. What is it? If you consider on the complex plane, it's the relation between 6 points on the plane. Okay? Distinguished gauge, in this case, when L, M, and N equal to 0, are the following conditions for structure constants. These conditions have very simple meaning. The fact that A and B equal to 1 means that points phi1, phi2, phi1, 2 are collinear. The same valid for these 3 points and for these 3 points due to this constraint. Now, from these equations, one can show that phi1, 2, okay, this is trivial, somehow obey the following constraint, following relation, and due to the associativity condition I wrote before, we have the following relation between all these coefficients. This meaning of these relations again, that point phi1, 2, phi1, 3, phi2, 3 are collinear on the plane. So we have 4 sets of 3 points which are collinear on the plane. It's just classical Menelaus configuration, 2000 years old, and the form of this configuration is given by the following picture, 1. So all these points are intersections of 4 straight lines on the plane. Okay. From a relation for function phi, we have one can find one can express all a, b, c, and so on in terms of phi in the following form, and then substituting this expression for a, b, c into this associativity condition and rest, one can show everything is reduced to the single equation for phi. So this is nothing but the associativity condition written in terms of phi. And this is a famous Menelaus relation between 6 points on the plane. For these 6 points, of course, always satisfied, but the statement is not that trivial, of course. This condition, if we have 5 points, point phi1, phi2, phi1, 2 collinear, then the points 2, phi2, 3, phi3 collinear, and then we have 2 points phi1, 2 line on this line, phi2, 3 on that. This condition guarantee that point 1, phi 1, 3 lie on this line and collinear with points phi 1, 2, phi 2, 3, phi 1, 3. This is just condition of collinearity, very strong. So it's necessary sufficient condition. Okay. What I showed here, in fact, that this relation is nothing but the associativity condition. So it was just associativity condition written in terms of phi. Menelaus relation is very old, 2000 years, one can find it, all books in geometry. Recent development was that it was shown first by Neichel, then by Bogdan and myself. It's a rise as a nonlinear superposition formula for Schwarz and KP hierarchy. And interpretation, connection with the Menelaus had been found by Wolfgang Schiff and myself. And then it was shown that if you will describe deformation, we will have so-called Menelaus lattice on the plane. And in fact, before I discussed just associativity conditions, well, okay, if you write down a discrete system of deformations, we have the following system, which exactly coincide with the conditions found by Wolfgang Schiff and myself, and describe Menelaus lattice on the plane. Well, I have almost no time. Now let's consider another gauge, where these sums are equal to 0. One can show that associativity condition reduced to the following single equation. This is equal to 0 identically. Linear equation has the following form.
Your gauge transformation does not change algebra. The algebra is isomorphic, yeah?
Sorry?
Algebras are isomorphic to the different gauges.
Original algebra. Original algebra, yes.
So the gauge is just a choice of basis, yeah?
What? Sorry?
The choice of gauge is a choice of basis in your algebra.
Okay. Yeah. Well, okay. Write down the system. Central system one can show, one can obtain standard way, is equivalent to the following system of 2 equations for A, C, and E, and the associativity condition. So it's simplified drastically. Very special property. Okay. This equation one can meet in many places. It immediately implies the existing function tau such that a, c, and a are the following form, with arbitrary constants here. Now, if we will substitute this expression for a, c, and a in associativity condition written above, that one, we will end up with the equation which everybody knows. It's just nothing but the Hirota-Mew equation for tau function of Kp hierarchy, or addition formula for tau function of Kp hierarchy. What I would like to emphasize here is nothing but the associativity condition for our algebra written in terms of function tau. In other words, it's nothing but the central system which describes the discrete deformation of our algebra. Well, like in Menelau's case, we can ask about what is the geometrical meaning of these configurations in this gauge. Again, let's write down the full system of equations. Okay, what does it mean, this equation? That point 1, 5, 1, 2 lies on the line which passing from through points 5, 1, 5, 2, okay? And line, no, it's written here. Through a region and parallel to the line passing from through points 5, 1, 5, 2. The same is valid for these 3 points and other 3 points. Okay? One can show, it's almost obvious. Then we have the following relation between 5, 3, 5, 1, 2, 5, 2, 3. And then now let's remember the associativity condition, that one. This implies that these 3 points are collinear. So we have what we have. We have the 6-point configuration on the plane. These points are collinear, that points not. In fact, we have the following configuration. So we have this arbitrary points 5, 1, 5, 2, 5, 3. This is a region. This line is parallel to that one to this, and so on. And these lines, points lines on these lines, and they are collinear. This is Kp configuration. In Menelau's case, we have a configuration of 6 points, which is classical. This I didn't find in classical textbooks, but probably should be known somehow. But anyway, it's connected with the discrete Kp, Hirota-Mew equation. Well, one can continue and ask the question, what is the connection between the points, 5, 6 points involved? One can show the following equation, very well known for superposition formula for Kp, dual Kp wave function, first found by Frank Nijhoff and then reproduced in many ways. Okay? Moreover, one can show, and I should skip all that, I'm sorry, and ask 5 minutes more, probably. One can show that Menelau's configuration and Kp configuration are closely connected. They're really gauge equivalent to each other by a special gauge transformation, not very complicated. Gauge function should be a Kp wave function. Okay? Well, so now one word about the possible multi-dimensional extension of all that. I consider 3-dimensional case, so I consider subalgebra. Now let's go back to n-dimensional algebra where J is different from K. Again, let's impose this Menelau's constraint. Associativity condition give rise to the following system of algebraic equations for A and B's. And one can show immediately that this system implies the following cubic relation. And from this cubic relation, one can derive the following formula, identity. Okay? Let's try to express A and B in terms of phi from this equation. It's easy to do. And then what we will get is the following relation. This is nothing but the n-point extension, n extension of the Menelau's relation. In fact, it describes situation, it was found quite recently in geometry, strangely. In Menelau's case, we have had a triangle crossed by a straight line. Here we have n gone crossed by a straight line. And then these are distances between the points. So f1, f2, h3 up to fn are vertices of the gon. f1, 2 in point of cross section of straight line with the side 1, 2, and so on and so forth. And we have the following relation. We have exactly the same meaning as the mini-laws. It's again associativity condition for our n-dimensional algebra. Okay. In central system, what we will get, I shall not write it exactly, give rise to deformations of these n-gons. One known that in fact this relation, if we choose these points as a parameter fixed, is nothing but the Hirota equations on quad graphs, which has no some specific property, Teheteron property. Okay. Now in KP case, KP gauge, same n-dimensional case, we have similar results again. Impose this constraint, this associativity equation. Again, one can show that it will give us a multi-component KP, multi-dimensional KP configuration. Central system is the following system of equation. Algebraic associativity condition Z1. Again, it applies the existing tau function, and the whole system is reduced to this n-dimensional KP, Hirota-Miwa equation for KP hierarchy. Well known. Well, okay, so to finish, I might have more than 5 minutes from that point. We have seen that addition formula for tau function is nothing but can be treated in this approach as an associativity condition for certain algebra, parameterized in terms of tau function due to the central system, due to the equation for deformations. And of course, it was mentioned already by Professor Krishevich that there is strong direct connection between tau function for Kp and theta functions. So it's quite natural to ask, can we treat this phase trisecond formula as a sort of associativity condition? Not going in details. I would like to show it's exactly the case. Okay, formula has been written before. So again, let me have Riemann surface, theta function associated. This is a EXI denotes the prime form, all is defined here. Phase trisecond formula, one of the form, probably original one, is the following. So the products of theta function, different points, omega is this is vector, forms the basis of holomorphic differentials. These are just nothing prime forms, and their integration, there are 4 points involved. And this is phase trisecond formula. I'll try to rewrite it in different form using the following identity, standard identity for these integrals. One can show that phase trisecond formula is exactly this one. Instead of integral from alpha 1 to alpha 3, you have the difference. The rest is the same. Now, let's try to treat it. Let's fix alpha 0 and alpha 1, alpha 2, alpha 3. Let's denote these integrals for given alpha 1, alpha 2 as this in U. Of course, again, it has been used in the previous talk. It's a well-known thing. Okay? Moreover, let's consider the shift of argument on theta function as the shift. Okay? We have 3 vectors, so we have 3 shifts. Then the previous formula, that one, can be rewritten in form in terms of shifts. Okay? Prime, this constant do not depend on that. Now let's apply to this relation T1 to all terms. Here T1 minus here and so on and so forth. What we will get? We'll get the following relation. And one can easily recognize the same formula as I wrote before for tau function, where alpha, beta, and gamma are these products of prime forms. And as we have seen before, is nothing but the associativity condition for specific algebra, where the products, okay, it's written here, of this algebra And this is just associativity condition with the following parameterization of A, C, and A. Probably it's known. This will be my question. I didn't find it in literature. So phase tri-second formula can be considered as an associativity condition for certain algebra under certain parameterization. In other words, if we will consider discrete deformation of this algebra, okay, I introduced before, phase tri-second formula is nothing but the central system describing the discrete deformation. And here, of course, one can ask a question, and probably the question will be really stupid. I'm sorry in advance. But we already wrote the linear system associated with this algebra is that one, okay? Now, okay, I forgot to say, in case of Kp, we assume that A, C, and A are real valued, and we have this configuration. Now, of course, A and C and A should be complex valued. Nevertheless, we have the following equation. Associativity equation implies that points phi 1, 3, phi 1, 2, phi 2, 3 are collinear in some sense, okay? Because the sum of coefficients equal to 0. And using standard formula written, presented in the previous talk, for instance, for function phi, which is wave function, one can say what? These points can be represented as the ratio of theta functions. So somehow we have these ratios correspond to collinear points. And my question is, what does it mean? And is there any connection with this collinearity in the Kummer variety? I have no answer. And if you will allow me, I would like to say something about the connection of associativity and 3D consistency, because it could be of interest for several persons here. Okay, let's rewrite again the system of equation, okay, with 3 indices. This is algebra, system of equation. Central system we already wrote down. It's 3-dimensional, truly 3-dimensional system. Now let's calculate equation about the reduction. Can we reduce this 3-dimensional system to 2-dimensional one? Very natural question, very well known. There are a number of answers a different way. For instance, through symmetry constraint or potential wave function constraint or symmetry constraint with symmetric some functions. What we have to do? We have to impose constraint on the coefficients here, A, B, and C. What type of constraint? We would like to have 2-dimensional system. This means we should assume that AJK is a function, certain function of Fj, Fk, and phi. Phi j, phi k, phi. Similar for B and C. Here, all indices are distinct. This means that A1, 2 depends only on phi 1, phi 2, phi. Phi A1, 3 will be function of only phi 1, phi 3, and phi. Okay. I would like to have constraint of that type. Do they exist? It's a good question. But if they exist, what we will end up with the following equation for fixed indices j and k. Pair of indices could be 1, 2, 1, 3, 2, 3. And now we see this relation between 4 functions. Phi, phi 1, phi 2, and phi 1, 2, for instance. Or phi, phi 1, phi 3, phi 1, 3. And it would be natural to ask, since the original system is completely symmetric with respect to exchange of indices, I would like to ask all these systems just coincide in the pair of indices 1, 2, 1, 3, 2, 3. Okay? Naturally to ask. Of course, there is additional requirement we should respect. We have the central system, a system which describes deformations. And of course, the constraint, a reduction should be compatible with the central system, of course. How to construct, I will not discuss, but nevertheless, I believe it's for those who studied 3D consistency, it's quite clear that procedure I just described is just inverse to procedure which is called usually a 3D consistency or consistency around the cube. Why? Because in this 3D consistency approach, they start with the equation on the quad graph, equation for 4 points, 5, 5, 1, 5, 2, 5, 1, 2. Then they assume that there exists virtual third dimension and write down the analogous equation for third direction, substituting just solutions. These functions basically are the same, only difference could be just in parameters. Okay? 3D consistency in the approach, as I understood, means exactly that one. You take first equation 5, 1, 2, 5, 1, 2, apply it, shift in third direction, you have this one, do similar with this in that equation, and the results should be the same. Consistency around the cube. And you see this requirement is what in procedure I described was original requirement of associativity or consistency, compatibility of linear equations. So I would like to say that 3D consistency condition is nothing but the associativity condition for this particular algebra I described before, exactly this condition. And to try to convince, I'm finished, I'm sorry. I would like to present some simple example. Okay. Take linear system which corresponds to the BKP case. That one, well known. A, again, the following form. And discrete system, one can show it is nothing but the Hirota-Miwa equation for BKP hierarchy. It's again discrete system. Central system which describes discrete deformation of algebra with this specific constraint. Now, due to my approach, I will impose constraint on A. So AJK I will choose in the following form where alpha j, alpha k are constants. What I will have under this constraint, substituting in the linear system, I will have the following equations for any pair of indices j and k. Okay? And one can show, it was shown, that with this under this constraint, central system means this equation, BKP, Hirota-Miwa equation, is satisfied due to this equation, using the fact that tau function should have the following equation. This is just consequences of that. So it's shown that under this constraint, BKP, discrete equation, so Hirota-Miwa equation for BKP hierarchy is reduced to equation on quad graph, and this equation is nothing but the H1 equation for ABC list. Okay, this equation has an interesting geometrical interpretation inside the geometrical interpretation of the BKP hierarchy with reciprocal triangles, or even simpler in some special quad graph with special property with a fixed area. And really to finish, I would like to take a look on this letter, Q4. People in quad graphs, all that will say, okay, this is the most generic case. Well, I write down this system of 3 equations I wrote before. Reduction to Q4, one of the possible reduction, is given with the following formulas. A12 and B12 are given by this, where A, B, C, and Z are just simple polynomials. And similar formula with exchange of x2, x1 for A1, 3, and so on. And one can show that the system of 3 equations here, written above, is reduced for Q4 for x, x1, x2, x1, 2. Is it admissible reduction for this central system? It's for me still open question, because do it by hand is almost impossible. But I believe so. So this example shows that, for instance, that this process of reduction, I believe, can reproduce equation on integrable equation on quad graph and something else also. Now I'm finished. Thank you very much. I'm sorry.
Any questions?
how do you find the constraints?
Sorry?
How do you find the constraint? Do you have some trick to find the constraint?
I mean this ansatz?
Yes.
Very simple, in fact, because, no, in fact, it's simple, even trivial. We see, constraint reduction should be ratio A, B, and C on this function should be rational functions of x and 1, x2, x3, and so on and so forth, clearly. If you would like to have Q4, Q4 is the relation between x and 1, x1, x2, x1, 2, which is polynomial, linear with respect to each variable, very specific form. Okay? So I would like to have that this equation after such a substitution will give you Q4. And if you have the equality of polynomials of 3 variables, and the rest is just simple calculation to show that this A should be linear, B should be linear, this should be cubic, and Z should be of that form.
And you believe that when you put your central condition, then you have all these parameters 8, 1, 2, 8 tilde will become.
I believe so. No, I didn't do this calculation, but I believe so. It would be strange, it would be not a case, on the other hand. It would be strange. Of course, calculation will be not easier, not much easier in the original case of Adler, I believe, but it would be strange it wouldn't be the case. Because this type of constraint should have some meaning, like a symmetry constraint. Unfortunately, I have known any meaning of that. And I would like probably you and Frank, somebody else can help me. In symmetry constraints, there is very natural and clear procedure which guarantee that these symmetry constraints are compatible with the original system. Here, I don't know. In the H1 case, I showed it. In other cases, no, it should be analytic calculation, very easy. I mean, for a computer, it should be in 1 minute you will have answer. Yes or not?